Hello, my name is Matt Levi, and I'm an assistant professor of soil science at the University of Georgia. I'm going to present some results today from a simple soil moisture model we're developing for high resolution predictions for large areas to inform wildfire danger. So we know that wildfire affects almost 150 million square kilometers globally each year. In the United States, that's averaging almost 40,000 square kilometers a year in the last 10 years or so, as we use the monitoring trends and burn severity data set. We can see that since 1984, the areas burned in the US seem to be on the rise. And most of the areas that are burning are focused in the Western United States, with some pockets across other parts of the country. So oftentimes when we think about the interaction of fire and soil, it's pretty common to ask the question, well, what happened to the soil? How bad was that burn? Let's think about erosion. But if we try to flip this on its head and say, how can the soil inform the fire prediction? That's what we're really focused on right now. So if we want to predict fires, we know that some of the traditional predictors are climate variables, fuel condition, fuel load, etc., ignition sources, topography. We could add wind speed here and a number of other predictors. But if we really try to understand something new here about what can we use to predict fire, then we might insert the soil profile as a new variable. So the soil profile is especially important because it has this memory of climate, and it sort of holds this soil moisture as a sponge, if you will, to feed into the fuel components. So the fuel type and the fuel load in a given year or season. So we think that soil moisture is really important for trying to better understand the fire likelihood predictions. So we have pretty good soil information for some parts of the world. And there's this balance between soil information at a global scale, like this soil moisture active passive soil moisture representation with respect to scale and the temporal information. So here we have a 3-day composite. So this is really great if you're modeling at this scale, but if you are wanting to model at a different scale, there might be some challenges using that information. So these satellite-based products like SMAP and SMOS, they often focus on the surface, even though we do have the ability to predict within the root zone from that pattern. Also, we have, most of our satellite-derived products are somewhat recent that don't necessarily align with the fire information that we have in our records. So another option might be to use point data from some of the Mesonet stations across the country. You can see that some states have really excellent distributions of soil moisture information and climate information, whereas others do not. So that presents an issue with the scaling of this information. And how do you connect these points in some zones to fires in adjacent areas? There are other products available, including something like the SMERGE dataset, which is a daily root zone soil moisture product, which does have a longer record of information. But again, we have a limitation of spatial scale. So the pixel size is 0.125 degrees. So this may be more challenging to apply for zones that might be more localized in terms of wanting to predict. So we have also a number of land surface models that we could use where we kind of turn the dials on precipitation and evapotranspiration, trying to take into account soil information and landscape as well. So here we're kind of limited in what kind of data we have to use as inputs to those kinds of models. So our objective was to develop a soil moisture product or prediction model with detailed spatial, temporal, and depth resolution that might be optimal for fire risk assessments to really inform fire management decisions before and after fires. So we utilized the Newhall simulation model, which is a simple water budget model originally designed for monthly climate soil information, mainly used for soil moisture regime assignment and soil temperature regime assignment from the USDA NRCS in terms of soil taxonomy. So it works really well, has been used and applied for 20 to 30 years for that purpose. And so this 8-layer soil profile model has worked well for that application. It's written, right now it's written in Java, so we've taken that and put it into the R framework to allow us to do some modifications of these cost layers to think about how soil moves through the soil profile. Some of those improvements include changing the time step from a monthly model to a daily model for soil moisture prediction. And so to do that, we're utilizing gridded products for the meteorological information, including Prism, and we're actually incorporating MODIS ET as well. So the soil profile has now been expanded to a 10 by 10 grid instead of an 8 by 8 grid. This makes it easier to scale different depth increments and make it more sort of intuitive to understand. It allows us to incorporate different soil physical property information for each depth increment or slice from the dry end of the spectrum with the wilting point noted here all the way to the moist end or the wetter end of the spectrum. So we've tried to account for this continuum of dry to moist conditions, mainly relying on soil physical property inputs that relate to water holding capacity. It's designed right now to utilize inputs from the gridded Surgo soil survey product, but it could incorporate other information from different sources if that was available. So the study area we're working in right now is the Red River watershed. This is a large watershed that spans approximately 93,000 square miles. Here, the mean annual precipitation ranges from approximately 17 inches in parts of New Mexico and the panhandle of Texas, all the way to portions of Arkansas and Louisiana with close to 67 inches of mean annual precipitation. So there's a wide gradient of precipitation and vegetative zones across this region. And importantly, there is also a significant fire occurrence within this zone. So we wanted to first start developing this model from a daily time step using point information from Mesonet sites. We relied heavily on the Oklahoma Mesonet for the development of the model. And so here you can see an output from one of those particular locations at different depth increments in the soil. So we have a 0 to 10 centimeter slice and a 20 to 30 centimeter slice represented. You can see the field capacity and wilting point noted here on this volumetric water content scale for the year 2009. The modeled values of volumetric water content tracked pretty well with the measured values. So that gave us some confidence to think that the model was working pretty well. So the next step was to look at this spatially to try to understand how well the model was working and in the context of a landscape. So here what you're seeing is Pearson correlation coefficients of the soil moisture active passive satellite data in the root zone. This is volumetric water content from 0 to 40 centimeters. Okay, and we're comparing that to the rNewhall volumetric water content prediction for the same depth. This is for the year 2016. So essentially every pixel, which were all resampled to the resolution of SMAP. So we're 8 kilometer pixels. Each pixel, we're looking at the daily correlation across the year for 366 days of the 2 different moisture products. So we can see that in the wetter zone of the watershed, we have higher correlations. So we're tracking a little bit better throughout the year. But actually in the zone where we have about a 500 to 600 millimeter precipitation threshold, the correlation starts to weaken a bit. So that gives us some ideas that the drier landscapes may be a little more challenging to model with the current approach. So if we try to understand what's going on there, looking at the temporal predictions of volumetric water content, here we can see again the comparison of the SMAP data and rNewhall and by depth. Okay, so we looked at different depth increments to 1 meter. Here again, we have the correlation coefficient on the y-axis and the day of year for the year 2016 on the x. So this red line here shows this correlation between the surface SMAP product and the 0 to 10 centimeter Newhall. We can see the correlation is relatively weak with a lot of variations from day to day. As we incorporate more of the soil profile, here with a 0 to 40 centimeter slice compared to the root zone SMAP product, a 0 to 70 centimeter increment, and the 0 to 100 centimeter increment, the correlations get a little bit stronger. And then we also notice the seasonality where things start to warm up and the summer months and the correlations are dropping. So this is going to at least give us a little bit of understanding about which depth increments are going to be tracking the known soil moisture from SMAP a little bit better. So the next step is to then try to apply this information for fire ignition. So to do that, we used a logistic regression framework where we're looking at, in this case, the growing season fires for the year 2016. So these data were derived from the MTBS data set as well as the interagency fire database. And so there's some range in size, anything bigger than 1 acre in size in terms of area burned. And so there's this trend that we're trying to understand, which is that the fire ignition points at a 14-day lag actually are showing wetter conditions than the random unburned points. And so this is a challenging thing to wrap your head around, mainly because we would expect that the soil moisture or fraction of available water would be lower, it would be drier for fire ignition to happen compared to these random unburned points. So we're still trying to understand why this relationship exists. However, if we look at fires from the same Red River watershed in the non-growing season from the year 2016 to 2018, derived from the MTBS data set. So all these fires are large fires. In this case, there are 36 fires greater than 1,000 acres. And if you look at different lag periods out to 1 year and a stepwise linear regression, we can see that the modeled area burned compared to the measured area burned in acres actually shows a promising relationship here. So we believe there is some potential for utilizing this simple soil moisture model to relate to fire size and potentially fire occurrence. In summary, the soil moisture predictions with rNewhall are comparable to the point data from the Mesonet stations, as well as the data predicted from SMAP. So that provides some useful information to help us apply to wildfires and other questions. However, the interpretation of that information for wildfire prediction is a little bit challenging right now to understand. So we believe that the challenge may be with respect to the point locations of the fire ignition. So in many cases, the monitoring trends of burn severity data, for example, uses a centroid of the area burned to indicate the ignition point. So this is a little bit challenging to relate soil moisture conditions, as you can see here, for 1 day in 2016 to wildfire occurrence. So really we need to apply the next steps here for looking at a longer record of rNewhall to compare more fire years to try to get a better handle of what's going on in this case. So I'd like to acknowledge financial support from the South Central Climate Adaptation Science Center, as well as the USDA Natural Resources Conservation Service, and contributions from colleagues Tyson Auctioner, Eric Kruger, Miguel Villarreal, Kevin Aching, and Rajendra Panda. Thank you very much.